So here's our lab now, and these are the libraries we are going to be using. So I'm going to be loading the survival, tidyverse, ggplot2, and car library. So survival is going to be for the lung cancer data set, and the car is going to be for the Levin's test. So I'm going to load this. So if you don't have it, ensure you install it before continuing. Then I'm going to be loading the lung. The lung is part of the survival data set, as you can see. So we have various survival times. So I think we check more on the lung data set and see an explanations of it. So you can see we have the institution code, the time, survival time in days, status, which is censoring, whether it is censored or dead. We have age in years, we have sex, we have PHECOG, which is ECOG performance score as rated by physician. We have ph.scano, that's Karnofsky's performance score. We have Kamovsky performance score as rated by patients. We have calories consumed, that means we have weight loss in the last 6 months. So these are the various data we have. So we're going to be using this particular survival data. I'm going to create new columns and convert them as factors: male, female, censored, death. That's what we're going to be doing now. So when I go back and check the survival again, head, lung. So you can see we have our status label and sex label. So we just converted the status, sex, and status variables into categories. We created new columns where we'll be converted into categories. So for the one sample t-test, now I want to check for the normality of the age. So I'm showing you how you can check for your assumptions if you want to conduct a t-test. I'm going to be using the ggplot, and I'm going to plot in a geom histogram with beans with value of 10, and I'm giving the age variable. So I'm going to run this, and you can see the age is almost normally distributed. So let me just change the value and see. So it's almost normally distributed, this particular age value. So it's almost normally distributed. So I can also use the Shapiro-Wilk test also to test. So the Shapiro-Wilk test, we have a p-value of 0.005. So this is for the Shapiro-Wilk test. So the Shapiro-Wilk test, the null hypothesis is that the data is normally distributed, while the alternative hypothesis is that the data is not normally distributed. So which means that normally in this situation now, we're supposed to reject the null hypothesis and conclude that the data is not normally distributed. But though if you see the graph is also showing like it is somehow skewed. If you can look at it well, maybe we could increase the bin size and see again. So you can see the graph is showing some sign of skewness, though it seems also to be normally distributed. But in situation, one can still proceed. So sometimes you can combine the Shapiro-Wilk test with the graph. So the graph shows like have the final say. At times you could conduct the Shapiro-Wilk test and it could tell you that it's not normally distributed, maybe due to some skewness which you can actually ignore. But the histogram could show you that it's somehow normally, though it looks skewed to the left, as you can see, but we could still make do with this, that is still showing some signs of normal distribution. So this is how the Shapiro-Wilk test actually works. We want to test if the mean age of people in that data set is 60, because we already have the age. So we already have the age already. We want to see if the mean age is 60. So what we are going to do now, we're just going to conduct a one sample t-test, which I explained in the last section, and we run it. And you can see that we are going to reject the null hypothesis that the mean age is not 60. So let's check the mean of our data set and see long age. So the mean age is 62.45. So which means we are rejecting the null hypothesis that the mean age is not 60. If we should use 62, what should we have? So you can see now that we are not rejecting the null hypothesis because the mean age is around 62. So we are not going to reject the null hypothesis because we are using what? The null hypothesis that the mean age is 62. So this is how the one sample test works. Now for the independent two sample t-test, now I want to compare survival times between male and female. So this is our survival times now. This is the survival time between male and female. So what we want to do now, you want to see the average survival time, is it equal between the two groups. So the null hypothesis is going to be that the average survival time of male is equal to that of female, while the alternative hypothesis is going to be that average survival time of male is not equal to average survival time of female. So now we're going to conduct the 11 tests for homogeneity of variance. So we're going to run this, and 11 test survival. So you can see that we have a p-value of 0.87. So the null hypothesis for the 11th test is that the variances are equal across groups, while the alternative hypothesis is that the variances are the various groups have different variances. So what this means now is that since we have a p-value of 0.88, it means we're not going to reject our null hypothesis, and that means that the variances are equal across two groups. So our data set already passed the 11th t test. So I already showed you, and sometimes it's not necessarily your data pass all the assumptions. You can also make do with some of the assumptions, and maybe like 3 or 2 assumptions. If you have that, you are also good to go. So I'm going to run this. So now let's conduct the t-test. So now this is how the t-test looks like, the two sample t-test. So this is an independent two sample t-test we are conducting, and this is our time. The time is the value we have, the quantitative value we are trying, and the various groups is 6 label. So we are going to be using the time, which is a quantitative variable, and by the various group, which is sex label, and data is the long data sets. I will run this, and when we run this, we have a p-value of 0.048. So 0.04861 is still less than 5. So what this means is that we are going to reject the null hypothesis, meaning that the average mean of survival times between the two groups is not equal. So I have the deep library. You can check my course on exploratory data analysis with R. So what I'm just going to be doing, I'm going to be saying long, and let me just call this long women or long men to be precise, and I'm just going to say long, and I'm going to be filter where the sex label is equals to, I think earlier on we gave it as male, so it's equals to male. So let me just turn this to long male. So, and we have long female also, where we say long filter sex label is equals to female. Also this, then we check for the mean of the long male. Sorry, we have to subset the time. Then we check for the mean of the long female. So you can see that the two mean is different. So which means these two particular groups are not, they don't have the same mean average survival time. So now we have the ANOVA group. So we have for the ANOVA. So I know you'll be wondering, what if I want to conduct a two sample dependent t-test? You know, we talked about that. So you could just check the t-test function now, and you have an argument here called paired is equals to false. So if you are using a paired data, you just make sure that your false is true. If you are using a paired t-test, just make sure you use argument paired is equals to false, which is by default you make it true, then your t-test function becomes a paired t-test. So this is how you can use the paired t-test. For ANOVA now, this is just age groups for ANOVA. So what we just did now, I just created an age group now, as you can see. In that is ANOVA now based on the age. Because if you look at the age we had earlier on now, the age was numerical. So I just used this cut function, and I use these breaks, this cut function, where I give my vector of variable, the variable vector, and I give breaks. So these breaks are the groups that is going to be created, and I give the labels. So group 0 to 50 is young, and 0 to 49 is young, and 50 to 59 is middle age, then 60 to 69 is senior, then above 70 is elderly. So when we run this now, and I called long the data set, long, so you can see the age group. So you can see the age group that we have now. So this breaks, this is, you can see from 0 to 50 is young, 51 to 60 is middle age, 61 to 70 is senior, and 71 above is elderly. So this is what this particular breaks means. When you run this and you call the long, if we were to call the long the long data sets, you can see that the age group here, you can see these are age group: elderly, senior, middle-aged, elderly. So this is what we actually have. So now we have 4 groups here, which means we can't use a t-test since it's above 2. So we're going to be using an ANOVA test. So to perform a one-way ANOVA of survival time across age groups, we're just going to use the AOV function, and we specify the quantitative variable, which is time. We want to see if their average time is equal. Then we have this age group. So this age group is now the variable that we're grouping by. Then our data set, which is long. So I'm going to run this, and this is our ANOVA table. We usually call this ANOVA table so that we can compute it manually, but if you have large data sets, this is something that is not going to be feasible. So we have what's called the F value, but we're interested in the P value here. So this P value is above 0.05, which is a level of significance. So this implies that the differences between those 4 groups is not significant. So which means we are not rejecting the null hypothesis. So which means you can't conduct a post hoc test. But let's say, for example, now the differences between the 4 groups was significant. So what do? We're going to use a post hoc test. So that's why I just put the code here to show you how to do the post hoc test. So this is a post hoc test, you can see. So if this p value of each of, now this is the middle group and the age group. This is the middle-aged and the young group. This is the senior group and the young group. This is the elderly and the young group. This is the senior and the middle-aged group. So this p value, if any of them is less than 0.05, it means there is a significant difference between that 2 groups. If, for example, now you can see all of them are above 0.05. Let's say this one was 0.01. Then it means that there is a significant difference between the middle age group and the young group. So this is what it actually implies. But you can see all of them are above 0.05, which means there is no significant difference. So this is just an example of how you can apply the post hoc test. And this is a visualization of the survival time by age group. So this is just a survival time by age group using a box plot. So you can see that the group, almost all of them are that their median, you can see the median survival time for each of the particular group are almost close to each other. There's no much difference. So that's why you can see that even our ANOVA show that there's no significant difference between their mean. Now, you can use the diagnostic plot for ANOVA to check for normality of your residuals. So you can use this to check for normality of residuals for your ANOVA model. So if this is almost a line of 45 degrees, it shows that is normally distributed, or if this particular curve is close to that line, it's just here it deviates, you can see. So this is how you interpret the QQ plots. So these are some additional descriptive statistics you can see. These are the mean age for male, the mean survival time. These are what we just calculate, and a standard deviation of the survival time. So this is just all about the various tests of means that we have, which are for this scope of the course. In the future, I might think of adding more advanced tests for means.